thanks again for joining us. Xuxin, take it away. Sorry, there's a pop-up. Okay.
Okay, should we get started?
Yeah.
Yeah, so thanks, Sacha. So I'm going to talk about visual whole body manipulation and locomotion for legged robots today. And let's let's take a look at this like long title for today's talk. So it mainly has four components: visual, whole body manipulation, and locomotion. So the top two, the left two is more like a method. So if you need visual feedback for achieving the task on the right, or if you need whole body control to achieve some like coordination between manipulation and locomotion. And whole body here, I specifically refer to like the coordination between like the robot dog and the attached arm. If there is like no attached arm or other mechanical structure, I don't refer to as a whole body control because if it's just a robot dog, any motion is more like a whole body motion. So the whole body here has specific meaning. Cool. So I'm going to mainly talk about four projects today. And the left two, deep whole body control and legs as manipulator, they are more like older project, and I will go through these two projects uh, more briefly. And on the right two, these are my like most recent two projects. Yeah. So let's take a look at the first one, deep whole body control. Learning a unified policy for manipulation and locomotion. This is a drawing work when I was at CMU with Zipin and Deepak. So what is missing from legged robots? So we have seen locomotion with impressive performance in the last decade or the last few years, with results in like challenging outdoor and indoor terrains. They can traverse like the rocky riverside, and they can go up and downstairs with ETH animal robot. However, there are some strong limitations to what a legged-only robot can achieve, since even the most basic everyday tasks, like require some forms of manipulation. So only like locomotion across different terrains are not enough for helping us on everyday tasks. This has led to the interest to building like legged manipulator. So there are some recent works on legged manipulator with an attached arm. So the main problems with prior works, the first one is like the learning-based locomotion and MPC arm control, which is like the leftmost one. There is no like very good coordination between the arm and the dog itself, because they are hierarchical models and they are like actually different paradigms. One is MPC and one is RL. And also the hierarchical modules will like introduce some black box control problems, which is in the middle of the slide. So this work they use a Boston Dynamics API to control the robot dog itself. So basically what it means is like they don't care about the low level control, and they directly call the high level API like for like walking forward, walking backward, and pitching up and down. And the arm is like a classic IK method. And the entire picking up pipeline is like planning based. Cool. So we hope to use like a lightweight single module to achieve this full body control that will not have like separate modules with complex MPC and RL in the same system. Okay, so why is whole body control necessary? Because actually the quadruped robot can stretch, bend, and roll like in all directions to expand the end effector's reach. But currently, the appropriate hardware is very limited. You either have to choose like Spot with an arm or some heavy animal robot with Kinova arm, which is very bulky and expensive. So we built our custom hardware with a very lightweight Go-on robot with a servo-based Widow X robot arm. And it's really lightweight with onboard computation and onboard power, and it's actually pretty cheap compared to those heavy kind of parts. Okay, so now we have the hardware, but it's still not straightforward to scale like the standard sim tutorial locomotion RL to whole body control. And there are mainly three challenges. The first one is height of control. So our robot showing the previous slides, it has total like 19 degrees of freedom compared to if you just want to do locomotion, it's only like 12 degrees of freedom. And this problem is exacerbated like in manipulators because the control is really dynamic and continuous, and you need high frequency control to achieve some high precision pick and place tasks. And this will lead to an exponentially large search space for RL to load. And the second challenge is conflicting objectives and local minimum. So basically what it means is that if we consider when the arm tilts to the right, the robot needs to like change the walking gait to account for the weight, the drastic weight like movement. The center of mass have moved a lot if the arm moves. And this will hinder the locomotion module and makes training prone to learn like only one skill for the policy. So basically the robot will learn either like only moving the arm or only walking on the ground. The third challenge is actually dependency. So if we consider picking an object on the ground, the arm actually depends on on the robot dog base to expand its reach range. So without the base moving, the arm on top of the robot is not able to pick something on the ground. So its workspace is very limited. So in previous works, researchers have used like curriculum learning to ease the mainly the dependency problem and the conflict of objective problem by like increasing the difficulty of tasks, so the policy can learn to solve simple tasks first and then tackle difficult set tasks. So there's a better chance to get out of the local minima of learning like only one skill for a coupled system. However, most of these like curriculum-based works, they still require many manual tunings of like a diverse set of curriculum parameters. And they also need some careful design of like automatic curriculum. So here, sorry. So here we propose to use a unified policy for learning both manipulation and locomotion. And to address the three challenges we just mentioned before, we propose to use advantage mixing, which is basically a very simple curriculum for our learning. Because we utilized a very important prior, which is that the manipulation tasks are mostly related to the arm actions, and locomotion tasks are largely depends on leg actions. So we can formulate this inductive bias in policy optimization by mixing like the reward for manipulation and locomotion. And eventually it's like if we write the RL PPO objective, it's like a mixture of two advantage functions. To overcome the symmetrical gap, we proposed the regularized online adaptation. So the main problem with like RMA was like we use the teacher to supervise the student network, but there's like no guarantee like the student can learn all the information uh, the teacher has. So there will be like an information gap or realization gap between the teacher and the student. Uh, uh, by like regularizing teacher network with student network along the course of training, we compress the two-stage training into one, and it reduces the realization gap by a significant amount. Yeah. So during deployment in the real world, we can have a few like operation modes like teleoperation or visual tracking or demonstration as commands as input to the policy network. To justify this, we want to show that first, the lag actions actually help the arm to achieve a larger workspace via bending and stretching the robot dog base to expand the reach range of the arm. So you can see if the unified policy actually achieves larger arm workspace. And the arm actually also help the robot balance. It has a like a higher survival score. Yeah, so let's also take a look at advantage mixing, like how it avoids the local minima problem. So with advantage mixing, it can learn like both. On the left side is more like a locomotion task. So the arrow is smaller for the blue line, which means that it learns to walk. And on the right is like end effector tracking arrow. Both policies can learn end effector tracking because this is more like a straightforward thing to learn. But on the left, no this automatic curriculum, uh, the robot cannot learn to walk. It will just stand in place and track the end effector goal.
Xuxin, can I ask a quick question?
Sure.
Can you go back? What do you mean by advantage mixing? Like, how is that advantage mixing done? I don't think that was explained yet.
I think I explained it here. So it's like a automatic curriculum. So previous curriculum, they are very complicated and need like manual tuning. And here we just add one parameter like beta to linearly increase from 0 to 1 through the course of training. So this is the only parameter you have to like tune or not tune at all. So what it means is like you learn locomotion skill and manipulation skill separately at first or at the early stage of training, and you gradually mix the objectives together so that it's like a curriculum learning for this control problem.
How do you actually train these separately here? So you've got like some agents in the simulation are have a
No,
different reward for being able to optimize.
no, we just have like two heads for both policy network and value network.
Okay, like what you're showing here on the diagram. Hmm. Okay, makes sense. Thank you.
Does that answer the question?
Yeah, just a quick one. So at what level of abstraction does the policy kind of operate? Is the output of the policy torques for both the legs and the arm, or joints? What's the output exactly?
It's all like position target for PD controller.
Position target for PD controller. Okay, thank you.
Yeah. Cool. Yeah. So with regularized online adaptation or ROA. Actually, there's the realization gap is order of magnitude smaller than RMA, and the survival score is actually higher. Which means that the gap is smaller, so the student, the teacher can also adapt somehow to the student.
Was that test there done in simulation or on the real hardware for that table?
Yeah, this is simulation.
Yeah, I guess you're going to get into some of the examples now, but one thing I always wonder about, I guess in this type of work, the whole body simulation and transfer will usually be more difficult for the sim to real transfer part. So maybe you can comment a little bit more on it when you get to there about how this particular design also helps enable that type of sim to real transfer. Because quadruped robotics is not too hard, but when we get into more manipulation and legs, it becomes more tricky.
Yeah, I think important thing is to match maybe the dynamics of the arm in simulation and the real world. So in simulation, you only have like a simple PD controller, but in the real world, different manufacturers, they have like different control methods for the arm. Some of them have like allows you to control the motor position. Some of them allow you to control velocity or like a torque directly. So you have to, if you're doing position control in simulation, you need to match like how the position control in the real world.
Okay.
Yeah, so they basically need to have like very similar or basically same control for the arm, because on the dog itself, I think it's pretty precise. You just call the dog's, PD controller is basically the same in simulation.
Okay, sounds good. Thank you.
Yeah, and here are some real world results.
Was the policy trained? In the simulator, was the policy also trained to pick up items?
No. So this is just like a simple illustration, like how our policy can act as actually a low level like controller and can adapt to different downstream tasks. This is just a like illustration of how well it adapts.
Okay.
Yeah, I'll go over this part quickly. Jump into next slide. Okay, so for the second project, this is about like if we don't have an attached arm, can we still like achieve some simple manipulation with the robot dog itself? So animals can use their legs beyond locomotion for some like simple manipulation tasks, such as pressing the button, open the door. And can we extend the agility of leggy robots beyond just locomotion? And yes. You can see it's actually a long horizon task with a few stages. The way we do it is to like learn two different policies in simulation, because the walking and like pressing button is like actually like pretty different for the RL to learn for one policy. And we use a mode in manipulation policy and a mode in locomotion policy to indicate like different behaviors. Also, because in locomotion policy, the walking mode is like if you are only walking, or if you are actually trying to climb the wall. And in manipulation, the mode indicates that if you are just balancing against the wall, or there's like a target for you to press. Here we use similar ideas to use ROA. And we added another like unified state estimator. The reason why we don't put this into the ROA framework is that our ROA can actually perform executing the lower frequency like 10 hertz, because the latent it is required to infer is like actually not changing like drastically. It's only like some static parameters like mass, COM offset, or friction parameter. But for actually you need some high frequency input to the policy, such as the velocity of the robot itself, which will operate at 50 hertz at a much higher frequency, and is changing rapidly. So we actually train two policies with two modes each. So there are like 4 sub skills in total, and in order to like stitch them together in the real world, we propose to like use the classical idea of behavior trees and adapt it to our like learning framework. In particular, it's like after training the level skills, we learn a behavior tree from a single clean demonstration of a real world demonstration from a human operator. It can extract the abstractions of skills into a behavior tree. And each skill are like conditioned on some visually matched preconditions. So the conditions can introduce like a recursive backing up behavior under unexpected interruptions. Yeah, this is a behavior tree execution in the real world. And again, to ablate the use of USE, or the unified state estimator, we compare the performance with and without USE, and you can see with the estimator, the network actually learns faster. And same thing, ROA reduces realization gap. Cool. Let's jump to the third project. So basically, this is the first project I've done in UCSD. Sorry, is there any question or something?
Yeah, just at least a short one for me. So you're introducing the behavior trees, which are great. I guess I was just wondering how easy or difficult it would be to edit the behavior tree. And if we want to add one more skill in there for some other options we want for the policy.
I think it's pretty easy, yeah, because it's being used in the game industry. So if you consider like PC games, there are like tons of different skills for each NPC or non-player character. So it's pretty easy to add new skills, and that's the one of the most important advantages of behavior trees for like stitching different skills.
Are they optimal orderings of the skills?
I don't know. So, okay, that makes sense, Xuxin, but yeah, do you want to ask your question? It's like 4 he's talking about? Okay. I doubt it. I'm not sure. I guess one of the questions that we have in the room is whether or not like the choice in putting together this particular behavior tree can find like optimal orderings out of the skills.
No, it just learns from like clean human demonstration. So human demonstrated once, and it will extract the behavior trees or the abstractions of the skill like sequence for once, and then you can execute it in the real world. It will automatically switch between skills then, based on what it sees.
Okay.
Yeah. Okay, sound good. Let's get into this this newer project. So basically, what we have seen before, we showed some like preliminary results on visual tracking, but with some like pretty hacky tags on the ground. But in the real world, there are no such tags. So how can we pick up these things automatically without like a tag? But the good thing is that we actually showed the low-level controller can be used for many downstream tasks. It can act as a very good low-level controller. So in order to complete this task autonomously without these tags, how do we design the visual feedback? And what is missing with mobile manipulation? So on the left is a paper that use spot robot and the spot arm to pick and navigate to like basically any place in a home environment to do pick and place tasks. And the problem with this is that there's no whole body control, which means that the robot stand in place and not moving and then pick and place. I actually went over like all the videos on their website, but I didn't find actually a pick on the ground. So basically all their pick and place are like either on a sofa, on the couch, or on a like higher surface. So but this is a very impressive result, which shows that the Lego robot can actually do these tasks, but it lacks the ability to like pick things like from different heights. And also this is like a complicated pipeline. So for the spot robot, they only have high level APIs we mentioned before. So they use RL to train some different modules and call the Boston Dynamics API when it's appropriate. They have a very complicated like condition when to call the Boston Dynamic API. So the pick and place, the pick action is actually completed by the Boston Dynamics API. And it's not working very well. So the R policy have to like align the gripper to center the object in the middle of the camera image, so the Boston Dynamic API can pick up successfully. And we also noticed there's no like such retrying behaviors, because it's very hard to accomplish with these complicated modules stitched together. So the right is more like a 3D perception paper, which injects 3D features into a nerve. So the robot can like can be queried with some text prompts, like wash my dishes, throw out my trash, and things like that. And again, there are like, this is more like a perception paper. There is no pick and place. So it means that the control is actually also very important for everyday task. And we have had like a lot of good representations both in 2D, like in the left image, they use some off-the-shelf static detectron like models to do detection, and on the right it's 3D. Yeah, so most recent paper, they also use a similar idea, but there's a robot actually doing things. It's pretty similar to clip fields. but the robot arm is actually picking up objects. And again, you have to like scan the scene in advance, and it's more like a static scene. But it shows the ability to like combine like large vision language model with the robots. And of course, the most recent mobile Aloha is it's really like dexterous and have some really impressive demos here, like taking a shrimp. And it actually can do some really fine manipulation tasks, like taking out a contact lens from from the package and put it on like a toy frog. But the problem with these line of work is like they have immense scaling costs. So it's basically imitation learning. If you actually want to accomplish more tasks, you have to like build more like setup like these and have more people to collect data for you. And it's also hard to generalize to the outdoor environment. So if you live in California, it might be better, but if really cold, so you don't want to like go out and collect data all day long. And the scaling cost also require, of course, a lot of money. So like if you have a lot of money, you can build a like Google, like a robot factory like Google, or a robot classroom where the robot will collect real world data. Yeah. So the question is how to like scale mobile manipulation with like the robots with a lower cost. Instead, we focus on the smaller problem of picking and placing objects, which means that our system may not do really fine manipulation like mobile Aloha, but we can scale very well with pick and place. And we utilize the latest teacher-student framework to overcome the symmetrical gap. So here we utilize the point cloud representation for the privileged teacher. So we add a lot of random objects, specifically YCB dataset during training, and have the robot to pick them up. And in addition to common like proprioception input, we also add the objects point cloud representation to the network. And in the second stage, we supervise the student with depth image and segmented masks. And in the real world, we use like AOT, or associating objects with transformers, which is like state-of-the-art object tracking algorithm, and segment anything model to provide like the same depth image and mask during training. And we have a lot of objects. In simulation, we mainly use YCB dataset, and in the real world, we have many out of distribution irregular objects also. So the shape feature is actually pretty important to help us scale like the number of objects it is able to pick up. On the rightmost, for the bowl and the drill, they are like more like a irregular shaped object, and our methods with shape feature actually achieves a much higher success rate than ours without the shape feature. Nice. And another benefit is that we have these kind of emergent retrying behavior. So if it fails for the first time, it can still try another round. So which means that you can actually move the object in the process of picking, which previous works, I think they don't have. Let's take a look at the video. fails for the first time, and then we try another round. So the putting like back into the basket. So the back and forth behavior are all like automatic behaviors. They're not controlled by remote. Ooh, is there any question about the previous project? Okay, sounds good. So let's jump into our last project of today. So if we only like have visual and locomotion, the two components, can we like push these two components to the extreme? So this is extreme parkour with like robots, with Koushil, Anani, and Deepak in CMU. So we have seen like vision locomotion, like in the past 1 or 2 years, achieving like really impressive results. Either it's like traversing stairs or doing some stepping stone. But these motions are like more conservative and it's pretty slow. The problem is, can we learn like a vision policy for more agile parkour task? It faces two main like problems or burdens. One is exploration burden. So you can imagine like if there is like a very high like obstacle in front of the robot may choose to like circumvent the obstacle instead of climbing onto it. So this is something with the RL. And another challenge is the rapid direction changes. So in order to do parkour, you have to like adjust your heading direction rapidly. Yeah. So let's take a look at the current is from Boston Dynamics for model-based control. And it may require some like fine modeling of the environment. I remember I saw the video of like how the robots construct a 3D representation of the entire environment in advance and do planning on top. So the ETH parkour project, we train like ask specific policies. So basically for each different obstacle, they train one policy and use like a high level navigation tool to select which policy to execute. Yeah. They also rely on elevation maps, and they are reconstructed by 6-step sensors. So it's very expensive to use. And you can also have some noise. They have some denoising network to denoise the constructed elevation map. The most relevant work might be robot parking learning. But the problem with it is that it has very complex curriculum. They have 3 stages. They also train like different policies for different obstacles. And yeah, individual locomotion policies can be distilled into one vision policy. And another thing is like they use a relatively simple obstacle abstractions as privileged visual information. What it means is that the robot during teacher training, the robot only like observe like the distance to the obstacle, the width and length of the obstacle. So it's like a few, it's a vector with a few scalars. So the abstraction might not generalize well to other obstacles. Cool. So let's get back to the challenges here. So in order to overcome the first challenge, we propose actually a very simple fix. It's actually a tweak to the reward. If we just use previous reward for velocity tracking, it will easily like learn to take advantage of the simulation and circumvent the obstacles in front of it. We do a very simple tweak. Like we take the inner product between the current velocity and the desired velocity. So in this way, if the robot is deviating from the course, it will receive very low rewards. And this kind of inner product reward can be easily applied to some other settings, such as stylized reward. So with this stylized reward, we can easily specify some other styles the robot is capable to do. So such as handstand. So in previous works, actually, in order to do handstand, you have to like learn a locomotion policy first and do some offline RL or fine tuning on top of it. So in the if we use just use this inner product based reward, it's very easy to get this kind of behavior. Yeah, this is comparison with and without this reward. Cool. So following previous work on teacher-student training, we also on phase 1 we train reinforcement learning from scanned out information, which is like more sample efficient. And in phase 2, we do dual distillation of direction and exteroception, which is the depth image. And here we do the latent distillation and the predicted heading distillation at the same time. But this will not work out of the box because the actor network, we actually do a deep copy here. So it's actually initialized. With proper heading command, the actor can actually walk around, which will look similar to the like a teacher policy in the simulation. But if the predicted heading command is like very noisy, it's initialized and it's learned. So this will lead to the policy like deviate from the expert course immediately. Like the robot will fall like in the corner in simulation and collect garbage data there because the teacher network can still like label the student observation. So we use a mixture teacher student, which means that if the heading command is actually it's actually too far away from the teacher policies course. We actually use the teacher policies action for this, and if not, we still sampled like the student action here. So this will cover like this will keep the advantage of Dagger and you know but it will not like collect too much garbage data. So the teacher student will learn nothing from predict heading. Okay, so with the above tweaks, we have some results. You can see the rear feet actually hit the front leg already in order to do a very long jump. High jump. The replay from the previous video. As we mentioned, this behavior is pretty hard to achieve with acceleration burden, but with this kind of simple reward, it's actually pretty easy to learn. And with this automatic like rapid action changes, it will easily fail on this ramp environment. And we actually use like default real sense camera on the A1 robot. It's actually working pretty robustly during a pressure test. It's not very good, but it still made it. Okay, nice. Here are some quantitative results compared to some baselines and the most recent concurrent work, robot parkour learning. And our robot achieved like the highest success rate. So in this project, we mainly introduced the dual distillation method, where we like distill both the action and the heading command at the same time, and the simple inner product reward that overcomes the exploration burden. And by using these tool, we achieved like extreme behaviors with such a small robot. And we also like open sourced the training code. You can train like in less than 20 hours on a single 3090 GPU. Yeah, here are some future works. Yeah, I think that's all for my talk today. Yeah.
Thanks so much, Xuxin.
Thank you.
Yes. Okay. Any questions?
Any questions from the people online?
All right. Okay.
I mean, I guess I've got a quick question at least. Because you were doing one of those final distillation steps in the last project for extreme parkour. And you were talking about how important it was to get the control to be the same for the robot arm earlier to make sim to real work well. But now you're adding in depth sensors and being able to get that to transfer well. So how much work did you have to put into getting like the simulated depth sensor in Isaac's gym to look like the sensor from like the real sense?
I see. I think after like you have set up the entire pipeline, there are actually not many tricks. You just have to like align the the parameters of the depths in simulation and the real world well. Like by that I mean like the position of the camera, like the exact position of the camera. Of course you randomize to some extent in simulation, but you still need to like tune that parameter well. And also like the clipping parameters, like how you like clip the depth image to a certain size in simulation, because in simulation you will want to have small depth images to save like memory, and in the real world you have to properly scale the actual depths to that size and clip, like do all the operations you do in simulation. And another thing is that you have to do some filtering in the real world, because the real sense depth image is very noisy. You have to do like whole filling, temporal spatial filter, all kinds of that. But I think for parkour is still like not as painful as like the previous project, like the visual whole body control we did, because for manipulation it's actually requiring it's actually having a like a higher requirements for depth quality. So for parkour I think it's still okay. So the robot, as long as the robot has a like a rough estimation of the obstacle, it will be able to do that. Yeah, for manipulation it's harder, and you need much better alignment with simulation. Yeah.
Okay.
But I think
Makes sense.
once you set up all in the entire pipeline, it's very easy to scale it to like to other, either it's like manipulation objects or more like parkour obstacles. Yeah, I think there's one in Zoom.
Yeah. Xuxin, you wanna?
Yeah, thank you for a very interesting talk. I still have some questions about this learning high-level skill sequences. So you get some demonstration first and then learn the behavior trees, right? I'm curious, what do you mean by demonstration there?
So basically you can use your remote to let me share screen again, actually. Oh, here. Yeah, can you see the screen? Can you see the screen?
Yeah.
Oh, yeah. So basically what it means is like the human operator will like use the remote to switch between different policies and different modes. As we mentioned before, there are like four modes. There are like two modes for each policy, and we have four subskills in total.
So,
And
so you mean like doing demonstration, the person who doing the demonstration need to actually select which mode the robot should
yeah,
perform.
yeah.
Right. So
Yeah.
how does the demonstrator know it is executable by the robot during the demonstration?
Sorry, what was that?
How do you know a particular demonstration is executable by the robot?
I think that for that part is pretty arbitrary. Like you think of a task the robot might be able to accomplish, and I have the robot to try that.
Okay. So in your experience, how many times do you need to try in order to get a demonstration that work?
I think it's pretty. I think one or two trials for these for the task on the image. You see, but for the tasks that require climbing the wall and use two legs to balance, it might be like 3 to 5 trials to get one like very good demonstration that is
Okay.
useful for learning. Yeah.
All right. Any questions? All right. That's it. Thank you very much, Xuxin. Great to have you here again. Thanks for this question.
Well, thank you guys. It's really great to be able to talk here. Yeah.
Good to see you again. Take care. Keep up the good work.
Yeah. Thanks.
Thank you.